Evening, sir.
All right. Good evening, Jamie.
Evening, sir.
How are you doing?
I'm good.
All right. Good to hear. Good to hear. All right. Know that your IA is due on which day is it next week? Tuesday.
Yeah. But the teacher, she told me it was today or yeah. She said she wants to see the presentation of data tomorrow
Yeah.
morning.
All right. No problem. So we're gonna cover a lot of stuff so you can start. Well, you already have your data to present now. It's just to put together the scatter plot and your diagrams. All right. So you don't have much more to do. Of course, I know it takes a lot of time to put together these graphs, so don't worry. All right, don't worry about it. So this is what we're going to cover today. So today we're going to be looking at linear regression. So just to go over into the syllabus right here. All right, going to the syllabus page. Just to go into the syllabus, we're right here. Investigate linear regression, understanding the concept of what is correlation, regression line, being able to find the R value, understanding what is meant by negative, positive, no correlation between two variables, strong, moderate, and weak correlation. Then we need to talk about scatter plots and regression lines of best fits. Then determine the equation of regression line using summary statistic. And then we need to be able to solve real world problems using regression. All right, so we're gonna complete this over the course of 2 days, today and tomorrow, but we're gonna get out the main part out of the way so you can start putting together, of course, your presentation of data to hand in. So first thing first, let's get into regression analysis. So look at this, Jamie. We're gonna start off with a theory first. All right, so look at this. Let's say we wanted to observe. Why is my pen not writing? All right, give me a second. Let's see something. All right. All right, I'm able to write now. All right, yes. All right, let's go. Look at this, Jamie. So we want to observe some relationship, right? Let's say we want to observe time spent on we want to look at time spent on game and see how that affect our grades. So we want to look at overall grades versus video game time, or the time that we spend on games, right? So what do you think would happen, Jamie? The more time you spend on the game, what should happen? Should, in theory, what should happen?
Let's drop.
Very good. So if you were to plot a graph, right, and on the x-axis is the video game time, what we're saying then is the more time we spend on the game, then our overall grade should drop. So let's say initially you don't spend no time playing game, your grade might be up here. Then when you spend maybe 2 hours a day playing game, your grades might drop to here. But if over time you start spend 8 hour, 10 hour a day playing games, your grade should drop. So we're saying this is You don't necessarily have to be in a straight line, but this is what we're saying should happen. Don't have to be in a straight line. The points can be all over the place. But just for clarity and keeping it simple, this is our grades. And this is video game time. So as we increase video game time, realize that our overall grades dip. Now look at this, Jamie. What if I gave you another scenario where we're looking at overall grades versus study time? So look at this now, Jamie. What if we're looking at overall grades versus study time? So the more time you spend studying, what should happen?
Grades rise.
The grades rise, the grades should increase. The less time you spend studying here, it's gonna gradually increase over time. Should increase, all right? It should increase. Remember, this is hypothetically speaking. We'd have to carry out the research and actually examine it. So hypothetically speaking, this is what should happen to our overall grade. Our overall grade should increase, all right? Now, sometimes now, there's just not necessarily going to be a relationship between two things. So let me try to think of an example. Maybe we want to look at, let me see, height. Maybe we want to look at a person's height versus the length of their arm. Because a lot of persons, they claim that the longer your arm be, then the taller you will be, and some crazy stuff. But in a situation like this, Jamie, this is just hypothetically speaking. There could be a possible relationship between them. But maybe you might find if you sample 20 persons, the first 20 persons, maybe you realize that the person's height and the length of the arm, maybe you're getting a lot of data here. Then the next time now, when you sample more persons, you get here. Then another time you sample.
Hello?
Right, Jamie?
You cut off for a bit or whatever.
All right, I got cut off for a bit. All right, my apologies. So right here, what we're saying then is, if this is what happening, right? We measure 20% and the average height round about here. We measure 60, it's up here, but measure 100, we say height drop down here. Then in a case like this, right, we realize that we can't make any conclusion from this, right? We can't draw any conclusion. Nice. So this is the whole idea of correlation now. We're trying to find out how, what's on the x-axis, we call it the independent variable. So it's just like physics. The x-axis, we're trying to see how the independent variable, affects the dependent variable. All right. So we're just trying to see how much does the x, whatever is on the x, influence what is on the y. So in other words, we see how if you play more video games, we see the negative effect that it's going to have. Grades is dipping. In that case, we say that this have what we call negative correlation. In this case, we say that the variables are negatively correlated. Negatively correlated means as one variable increase, the other one decrease. And as the other one increase, the next one will decrease. So notice, as grades go down, video game time go up. So game time increase. It's in the notes, Jamie. We're just summarizing right here. So In this case, we say this is negative correlation between the two variables. When both of them are increasing at the same time, this is what?
Positive.
Very good. Positively correlated. So as study time go up and overall grades go up, we say they're positively correlated. Positively correlated. All right. Then the next one is, of course, no correlation. No correlation at all. Right here, no correlation. No correlation. This is when we can't make any judgment at all. It's all over the place. So we can't make any correlation at all. That's where the idea of no correlation come into play. Now, as you can see in the syllabus right here, Jamie, right? There's different levels of correlations that we're going to talk about. We have negative, positive, no correlation. Then we have to talk about strong, moderate, and weak correlation. So now, Jamie, right? So sometimes, look what is happening right here. So let's go back. Sometimes what is happening is, maybe right here, maybe you plot a graph, right? Maybe you plot a graph for, let's say we're observing time that students spend studying at Bel Air and look at the overall grade. So study time in the evening, and this is what the data gathered. The data would have gathered maybe students studying for half hour, students studying for 1 hour, 1.5 hour, and 2 hours. Like nobody said they study over 2 hours, right? And then we look at the overall grade, and maybe majority of persons that study for half, averaging 70. Those who study for 1.5 hour, 1 hour, maybe averaging 74. Maybe those study 1.5 hour, they average 75. And those who study 2 hours, maybe average 90. Now, even though this right here, Jamie, even though this right here is positively correlated, we notice that, but wait a second. Let's say an exam question were to ask you to estimate, maybe estimate what somebody average would be if they studied maybe 6 hours per day. Now, in that case, you wouldn't be able to tell because your information that you got only had for persons half hour, 1 hour, 1.5, and 2. This is where regression come into play. Regression come into play, Jamie, where we'd have to know what we call the line of best fit. We'd have to find the line of best fit from these 4 points. So remember when you did physics, right?
So,
So when we did physics, we find our line of best fit. And what we try to do is get it so that most teachers tell you that you want it to be balanced. You want the same number of points to the left and to the right of it, right?
yes, sir.
Yeah, that's exactly what we'd have done in physics. Let me try and get this to be a real line of best fit. So try to get it so that we have it balanced on each, right? But it's not necessarily balanced on each side we wanted. Now that we're doing integrated math, Jamie, we're bigger than that now. What we're actually trying to do, Jamie, is to find a line that best describes every single data point. Every single data point, we're trying to find the best line that can describe every single data point. Hence the line, best fit line. Now that best fit line right there, what we're actually doing then is, what we're really doing is we're finding the deviation from each point to the best fit line. And what we're trying to do is find the average deviation from each point. So what we're trying to say then is, if this one average deviate from the best fit line 1, this one average deviate from the best fit line by maybe a half unit, this one average deviate from the best fit line by a quarter unit, and this one average deviate from the best fit line by maybe 4 units, what we would do is, to get the best fit line, we take the average of it, the average of these displacement from the best fit line, we take the average of it, and then we want to make sure that the best fit line will have the average of those displacement from it. So let's say we work it out, and I said this one was maybe 1 unit from best fit line, half, a quarter, and this is 4. Then what we would do then is we average that, 4 plus a quarter plus a half plus 1. Let's just say it worked out to be 6. 6 over 4 is 3 over 2, which is roughly 1.5. Then what we're saying then is the best fit line, we want each point to be roughly 1.5 deviations away from the best fit line. All right, that's what we're roughly saying. We want each point to be 1.5 deviations from the best fit line. Now this best fit line, it's gonna have an equation, because we said later on we want to be able to use it to estimate maybe what would be somebody average if they studied 6 hours a day. So this is where when we find that we're gonna need to be able to find the equation of this best fit line. Now this is how we're gonna find the equation of that best fit line, Jamie. So these are what we need to know now. This is where the real thing starts. Let me increase the font size. So equation of the best fit line. Now the equation of the best fit line, Jamie, is found by this. We call it y hat, meaning the predicted y value, because remember, really and truly is predicting where we're using our best fit line that's going to predict the possible y values based on the input x values. Because if you notice, the best fit line don't actually have on the actual points. So we use y hat because it represents the predicted y value. So y hat, and it's equal to a plus, or some persons like to say a hat. It doesn't matter, I like to just keep it a. But you might say a hat you're gonna say a hat on the formula sheet, you're gonna say a hat in textbooks. So let me write a hat. A hat b times x. All right? So y hat is equal to a hat plus b times x. It's just like the equation of a straight line, y equal to mx plus c, but we rewrite it as c plus mx, right? Just like the equation of a straight line, right? Now, the beautiful thing about this now, as I say, y is just the predicted output variable. In that case, we call it the dependent variable. A hat is the y-axis intercept. And then we say that b is the gradient. And x now is your input variable, or the independent variable. Independent variable. All right, cool. And don't worry, we'll so link everything to your SPA. Now, look at this now. After we do all of this, all right, we need to be able to find what is B. So this is another formula that you're gonna have to know now, Jamie. Now, the formula for B is equal to, it's equal to R. Don't worry about what is that R. Remember we were talking about R a while ago? I would say that R is just the distance, the average distance of all the points from the line of best fit. So this is the R value. So in order to find B, we're going to need to know the equation for R. All right? Now let's go. So B is now equal to R times the standard deviation of Y divided by the standard deviation of X. All right, that is how we're going to find B. The gradient is the standard deviation of Y times the standard of deviation of X. Now, Jamie, of course, in an exam, don't worry. For your SBA, you're gonna have to calculate everything from scratch, but in an exam, chances are they're gonna give you standard deviation of Y, standard deviation of X, and maybe they give you B and ask you to find R. Or maybe they give you all three and then ask you to find B. But in an exam, they'll never ask you to calculate everything from scratch. The only time you're doing everything from scratch is for your SBA. All right? Yeah, only time that you're doing everything from scratch. Where SY is the standard deviation of Y, meaning the standard deviation from the line of best fit, from each point to the line of best fit, to the standard deviation from each Y data point to the line of best fit. And SX, this is now the standard deviation from each X data point to the line of best fit. All right, cool. Now, Jamie, here's the next thing now. Now, as we said for the SBA, you're gonna have to calculate R, SY, and SX from scratch. Now, sometimes, yes, sometimes I give away 5 or 6 marks and ask you to find R. Yeah, man, sometimes they're giving away 5 or 6 marks to find R. All right, so this is another formula that you're gonna have to know. There are 2 formulas for it. So in the same way how you can find standard deviation 2 ways, I gave you a formula for group data and ungroup data. In the same way, you have 2 formulas to find it. Now, I like to use the formulas depending on what the question asks. So I'll give you the first formula. So the first formula is R. This is my preferred one. So this is the only one I teach my boys that do applied mathematics. So this is my preferred formula to use. So the preferred formula is to say R is equal to the sum of X minus bar X times Y minus bar Y over the square root of the sum of X minus bar X all squared. So X minus bar X squared, the sum of it, then it's multiplied by the sum of Y minus bar Y squared. This is my preferred format. This is my preferred formula to use. All right. Now the next formula that we're going to use is the one that's that is coming on the formula sheet. This is the next formula that they're going to tell us. The next formula is R is equal to n times the sum of X, Y minus the sum of X times the sum of Y divided by the square root of n times the sum of X squared minus the sum of X all squared. Put a bracket around this. Then all of that is multiplied by n times the sum of Y squared minus the sum of Y all squared. This one is on the formula sheet because they're expecting us to use this one, but I don't like to use it. All right. So of course, we're going to do it 2 ways, and you can tell me which way you prefer. And you can choose the way you want to do it in your SBA. Or let me close the bracket here. You can do whichever way you prefer. So for example, let me allow you to finish taking it down. So just going to show you here. In the notes, like a question like this from 2018, can use this formula. Doesn't matter. From the 2017 paper, You can use this formula, doesn't matter, to find R. But I'm also going to show you the other formula that we wrote down first. So you can choose which one you want. You can use this complex formula and do it, the second one on the formula sheet, or you can use the one that I like at the top. And they say, whoa, Jim using this formula? Nice. Up to you. All right. So that is that. So are you writing down these formulas?
Hold on, I'm taking a screenshot.
All right, no problem. All right, you got it?
Yeah.
All right, great. All right, now, Jamie, the next thing is, as I said, really and truly, it's just 3 formulas you're going to need. This one, and one of these to find R. But then there's another key thing too. Now we're going to talk about this R right here. So now, Jamie, remember we were discussing a lot of stuff. We were discussing that the grades can maybe increase over time as you study more. So in that case, we say that it have a positive correlate. We say that it have a positive correlation. Now, the positive correlation can either be strong, moderate, or weak. Now, Jamie would determine if it is strong. So in this case, we know it is positive. So we're looking at the positive cases first. Positive correlation. So there's a positive correlation, Jamie, but it can be strong if R square is between 0.7 but less than or equal to 1. This is when it is having a strong positive correlation. When R square is between 0.7 and 1. All right? That's when it's going to have a strong positive correlation. I like to remember it with the R square values. A lot of teachers might tell you when it has strong correlation with the R value. So if you were to square root 0.7, so a lot of teachers maybe write it this way. Let me bring up the calculator. Square root 0.7, that is 0.8. So in other words, a lot of teachers might say R needs to be between, R needs to be, the modulus of R needs to be 0.8. Meaning, in other words, R, it have a strong correlation, a strong positive correlation when R is between 0.83 and 1. But I don't like to remember the R values. I like to work with the R square. For some reason, the R square works so easier for me, then I can square root it. That's for strong correlation. I like to just remember R square values, strong correlation. And strong correlation just means that the Y value is heavily dependent on the X value. So we can make a strong statement, we can make a definite or a bold statement to say that these 2 variables are definitely strong correlation, and that's telling us that the Y value is heavily dependent on the X value. So of course, we're going to hope that in our SBA, when we do our calculation, it can prove our fact that wingspan and height, they have no correlation, right? Or we want to prove that, of course, it's not 1-to-1, right? So we're going to, of course, use our data to end up show that it's not 1-to-1 with our correlation.
Awesome.
Yeah, so this now is positive correlation, but strong positive correlation. Let's quickly run through now. Now, when the graph looks something like this, the graph, it's not so much proper anymore, right? In that case, when R square is between 0.7, less than 0.7, let me take off it, less than or equal to, less than 0.7, but greater than 0.3, we say that it is moderately positively correlated. So this is moderately positively correlated. All right. And finally, when it is r square, when r square is greater than or equal to 0, but less than 0.3, we say it is weak correlation. So very weak. Like the gradient barely going anywhere. All right. So when it looks something like that, still positive gradient because of how the slope is. But in that case, we say weak positive correlation. Now, finally, we want to know the nice part now, which is negatively correlated. I like negatively correlated questions because these are usually a little more challenging. So negatively correlated now, it's pretty much the same. This time now the slope is going this way, right?
So,
So when the slope is going this way and the r square value is still, remember, when you square any number, it's positive. Remember, Jamie, when you square any number, it is positive. So in other words, r square is still going to be between 1 and 0.7. In this case, we just say it is strong. It is strong, negatively correlated. And the rest continue. R square between 0.7 and 0.3, we say it is moderately negatively correlated. And finally, the last one now, when r square is between 0.3 and greater than 0, then in this case, we say it is weak negatively correlated. And that's it. Now that we go through all of them now we're gonna look at a question. How we're gonna apply all of this. How does it even make sense? Like, what are they saying to us? All of this, what are they saying? What are they saying? All right, let's see how we can apply it now to some questions. All right, I don't want to start with that one. Let's see. All right, here's a question now that we're gonna apply it to. All right. So this question right here, I like when we see it real life question, it says, anthropologists use linear model to relate femur length to height. Now, notice, Jamie, we cannot change what about ourselves? Can't change our height, right?
sir.
Typically, height in this case is going to be on the x-axis. So right here now, look at this. So an anthropologist use linear model to relate femur length to height. It says the model allows the anthropologist to determine the height of an individual when only okay, no. All right, so in this case, the question went on further to tell us what is our x. So most time they're going to give you what is the x. All right, so remember he's saying that the model allows us to determine. Another word for determine is what?
To find the
What word were we using today? Predict. To determine, so remember we started with that word right here, predicted output value. That's a y, right?
Yes, sir.
So I want you to always look out for the word the question. Once you set to determine, that's your y value. In other words, they're saying our y is the height of an individual. So they're giving us our y. The y in this case is the height. And then the femur length is our x. Now it says, from this question, we need to find a graph that can model this equation. Model all of these points. Now, Jamie, we're going to do it the two ways, all right? We're going to do it the two ways using the two formulas. So remember we said that y, all right, I need another blank document. Open the blank PowerPoint. All right, so in this case, remember though, while it's loading, write down the equation y hat is equal to a hat plus b times x. We know x already, but we need to find a hat and b. All right, we need to find a hat and b. Now, let's go ahead now and work this out. So first we need to find b, then we can always find a hat. So let's go ahead and find b. I'm just moving over to the PowerPoint. All right, so need to have the data fully here. 50, this. All right, I'm gonna have to look across every minute. All right, so just to write back down the equation, remember we said that B, the gradient B is equal to the standard deviation of y, r times the standard deviation of y over the standard deviation of x. That's how we're gonna find the gradient, that's our B. So now we need to find the standard deviation of y, the standard deviation of x, and we need to find the r value. Now what I'm going to do, James, is I'm going to create a table. When I have a table for our x values, then I'm gonna have a table for our x minus bar x. Then I'm gonna have a table for our y values. Then I'm gonna have a table for our y minus bar y. And then remember what the formula said. Remember the first formula we use in R is equal to the sum of x minus bar x multiplied by y minus bar y. Yeah, that's in the numerator over the square root of the sum of x minus bar x square multiplied by the sum of y minus bar y square. All right, so this is what we need. So we're going to need a column for x minus bar x times y minus bar y. That's that column there. Then we're going to need a column for x minus bar x square. I needed a little more space. We need a column for x minus bar x square. Then we're going to need a column for, yeah, the square won't work out. The square might not fit right here. I probably have to continue it around, no problem. So let's just write out the x and y value so we don't have to come back. 50.1, 48.3, 45.2, 44.7, 44.5, 42. Let's do it one by one. All right, so Jamie, can you like take a picture of this and quickly tell me the x values?
All right,
All right, thank you. All right, let's go now for the x values. So the x values were
50.1,
50.1. All right, next one.
48.3,
48.3. Next one.
45.2,
45.2. Next one.
44.7,
44.7.
44.5,
44.5.
42.7,
42.7.
39.5,
39.5.
38.
38. 38.0.
Yes, sir.
All right, great. All right, what are the y values?
178.5,
178.5.
173.6,
173.6.
164.8,
164.8.
163.7,
163 point how much?
7.
0.7.
168.3. 165.0. 155.4. And 155.8.
All right, so basically everybody's short. Just kidding. Basically, that's what this is saying. All right, so now we need to find bar x, which would be the average of all of these. So let's quickly do that around here. 50.1 plus 48.2, 40.3 plus, why this look like this? Why it's not erasing? All right, let's go. What? So why? I think 4 point is freezing. Yeah, let me just close out so it go away and go back in. Yeah. All right, just to find the average of them now. So add them up for me now, Jamie. Add them up for me. So I can find them. Just find the sum and tell me. Add these up. I can just write down the mean.
About 353.
353. All right, that is it. 353. Now, 353 divided by 1, 2, 3, 4, 5, 6, 7, 8. Divide it by 8 for me.
44.125.
44.125. I'll just say 44.1. All right, since most of it is 360. So 50.1 minus 44.1 is 6. 48.3 minus 44.1, what's that?
4.2.
1.2?
No, 4.2.
4.2. And this one? 45.2 minus 44. 1.1.
Yes, sir.
All right, the next one would be 0.6. Then the next one would be 0.4. And this would be negative what? 42.7 minus 44.
1.4.
Negative 1.4. Then this would be, what's that?
Negative 4.6.
4.6. And this one is?
Negative 6.1.
Negative 6.1. All right, thank you, Jamie. All right, now quickly, go ahead and find for me now the sum. Find out the sum of y. Find the sum of y. Let me take up my calculator so I'm not have you doing too much. $164.8 plus 163.7 plus 168.3 plus 165 plus 155.4 plus 155.8. That's 1,320. Did you get 1325.1?
So
All right, good. 1325. Point 1. And now we can divide that by 8, and I get 165.6. All right, in down. bar y is 165.6. In that case now, doing the subtraction, 178.5 minus 165.6,
12.9.
12.9. All right, the next one, 173.6 minus 165.6, that's 8.
Yes, sir.
All right, then this one gonna be negative for sure. 164.8 minus 165.6, negative 0.8. And this is negative 1.9.
Yes, sir.
All right, then this one is 168. Why not coming to me natural? That's 3. Don't reach 3. 2.8.
2.7.
2.7. Ah, yes, 2.7. All right, I definitely not going to do any more mentally. 2.7. Next one is negative 0.6, right?
Yes, sir.
Negative 0.6. 155, that's negative 10.2.
Yes, sir.
And this one is 9.8, negative 9.8, right?
Yes, sir.
Now we need to multiply these two. X minus bar x times y minus bar y. So 6 times 12.9, we're going to get 77.4. 4.2 times 8, we're going to get 33.6. Then 1.1 times negative 0.8, we're going to get negative 0.88. Then 0.6 times negative 1.9, we're going to get negative 1.14. Then 0.4 times 2.7, we're going to get 1.08. Then negative 1.4 times, wait, 0.4 times 2.7. Yeah, that's right. Then negative 1.4 times negative 0.6, that's 0.84. Then negative 4.6 times negative 10.2, that's 46.92. Then we have negative 6.1 times negative 9.8. We have 59.78. We'll add these all up now. Add these all up. And we're going to get 77.4 plus 33.6 plus negative, let me just put minus 0.88 minus 1.14 plus 1.08 plus 0.84 plus 46.92 plus 59.78. We'll add these all up, and I am getting that the sum is 217. Did you get 217?
I wasn't actually calculating this one.
All right, no problem. All right. Now, the x minus bar x square, you're just going to be squaring this one. Squaring that one. So that's 36. Then 4.2 square, that is 17.64. Then 1.1, when we square it, that's 1.21. 0.6 square, that's 0.36. Then 0.4 square is 0.16. 1.4 square is 0.14 square. I think that's 196 or 196. 4.6 square, 4.6 square is 21.16. And then 6.1 square is 6.1 square, 37.21. It's a lot of work. Now add this up now. 3.6 plus 17.64.
Sir, I
Yeah.
got 217.6.
0.6 to 17.6. Thank you. All right. Now add these up. We're going to get 36 plus 17.64 plus 1.21 plus 0.36 plus 0.16 plus 0.196 plus 21.16 plus 37.21. And I'm just going to keep it to one decimal place, 113.9. Now we need y minus bar y squared. I'm trying to squinge it here because it didn't make enough space. All right, I tell you what, I know what I'll do. We don't have to squinge it. I'll just remove this formula. No, but I won't be able to remove it. All right, let me see if it can fit. 12.9 square. Yeah, it won't be able to fit right here. All right, I'll just bring it around here then. So it's like the table continue. So y minus bar y square, that is this 12.9, when I square it, I get 166.41. Then 8 square, I know is 64. Negative 0.8 square is 0.64. 1.9, I know 19 square is 361. So that is going to be 3.61. 2.7, I know 27 square is 27 square. 729, I should have remembered it in a 729. That is 7.29. 0.6 square is 0.36. 10.2 square, I definitely don't know that. That's 104.04. Then 9.8 square, 98 square is 9,604. So we need the sum of it. So in this case, the sum is going to be, we're going to add these up. 166 point, yeah.
96.04.
96, yeah, 96.04. Yeah, thank you, 0.04. Nice. So now we add them up. So as you can see, Jamie, is a whole heap of work when you're actually doing it rough by calculation. But in the exam, you won't have to do this. This is just for your IA. So the first way, as I said, this is just for your IA. We're going to be using the other formula, which is shorter, but that's typically when you're in an exam because it's going to be like 3 marks. But for your IA, the other way actually is going to be longer than this method. All right. This is just for the IA. So that's 442 point. All right, 442.39. Let's just put 0.4. So now in that case, now we can go ahead and work out R. Now we can write down that R, which is the sum of x minus bar x times x minus bar y. So x minus bar x times x minus bar y, the sum of it is down here. The sum of it is 217.6. So we already get the sum of x minus bar x times y minus bar y. That is 200. I don't like the green. 217.6 divided by, now need the sum of x minus bar x all square. X minus bar x all square, that was 113.9. So 113.9 multiplied by the sum of y minus bar y all square. That sum was 442.4, and they will square root it. So we're going to work this out now. 113.9 times 442.4 square rooted and 217.6 divided by answer. So in the denominator, that part down here working out to be 224.5. And put this in the denominator. So 217.6 divided by 224.5, you get 0.969 or 0.97. So this is a what? This is which correlation, Jamie?
Strongly.
Strong, very good. Strong positive correlation. Strong positive correlation. All right. So if you were to square it, remember we were looking really with r squared. So if you were to square it, r squared would be 0.97 squared, which is 0.94. Once we have 0.94, we know that this is of course greater than 0.7. Once it's greater than 0.7, we know it's strong. It is strong positive correlation. Positive correlation because it's a positive R value. All right. So what this is saying is when both variables are increasing at the same time. So when X increase, Y increase as well. So here it is. The bigger the femur, the taller the height. So positive correlation. Now that we get R, we need to find the standard deviation of Y and divide it by the standard deviation of X. Now, you would have remembered we did standard deviation formula. Standard deviation, we said, is just the sum of X minus bar X. The sum of X minus bar X squared divided by N, right?
So
in this case, that was when we were just dealing with general standard deviation. But now in this case, we're dealing with standard deviation with X and Y. But the thing about this table is, once you find the R value, standard deviation easy. Because you just go back, sum of X minus bar X is right here, 113.9 divided by N. N is 1, 2, 3, 4, 5, 6, 7, 8. You do that. 113.8 divided by 113.9 divided by 8, you're going to get 14.2. That's the standard deviation of X. Then coming around here, the standard deviation of Y will be the sum of X minus Y, minus bar Y, all square, divided by N minus 1. Oh, I forgot to square root it. Sorry, square rooted. I didn't square root it. All square rooted. All square rooted. My bad, Jamie. Square root that. That's 3.77. Coming around here.
so why is it N minus 1?
Oh, sorry. N minus 1. Remember I said in most textbooks it's N minus 1. And N minus 1 is for very large samples. When it's 100, 1,000. Sorry about that. Right? So in applied math, we use N minus 1. In integrated, we use N. So from time to time, you may see me write N minus 1. My apologies. It's because that's when you're dealing with large samples. But you don't need to ever use N minus 1, all right? So let's go. So now we have the sum of Y minus bar Y squared over N. That will be sum of Y minus bar Y, Y minus bar Y, here it is, 442.4 over 8 square rooted. We'll put that in the calculator. Now square root it, so that's square root 55.3. I'll get 7.44. In other words, we're saying that the gradient B is going to be R times standard deviation of Y over standard deviation of X. In that case, it's 0.97 times 7.44 over standard deviation of X is 3.77. Finally, we'll finish. So 7.44 divided by 3.77 multiplied by 0.97. We're going to just put all of this in our calculator one time. And I get 1.91. So that's our gradient, 1.91. Nice. Now, once we get our gradient to be 1.91, yeah, man, so imagine you're going to do all of this for your calculations, in the SBA. Fully powered, don't it?
Yeah, I need to
And,
do
and,
more.
but then again, you're doing it in groups. So I would recommend maybe you can let your partner, maybe you do the standard deviation. No. Maybe you can do the calculations and she plot the graphs or something. But don't stress yourself. Make sure you give her some of the work and you don't feel burdened. All right?
Well, sir, I can't really do that because I have to show it tomorrow morning.
Oh, yeah.
I have Excel where you can just drag and we'll do all the formulas.
Okay. Oh, yeah. So you'll be fine. You just put in the formula function and then
Yeah.
work out. Yeah, no problem there. All right, now that we find B, remember we said the equation of a line is y equal to y hat is equal to a hat plus bx. Now that we know B, look at this. We're going to use a sample point to find a hat. It doesn't matter which sample point to use. I like to use the first one, so 50.1 and 178.5. So in that case, when x equals 50.1 and y equal 178.5. In that case now, we can just go ahead and say 178.5 is equal to a hat plus b, which is 1.91, times x, and x is 50.1. So transposing for a hat will be 1.91 times 50.1 is 95. So that's saying a hat is 178. Let me see, bring that over 178.5 minus, or multiply these two, we're getting 95.691. So we end up get a hat is working out to be, I'm keeping it to 3 significant figures, 82.8. That's a hat. A hat is 82.8. In other words, we're saying now then that this is the equation y hat, is equal to 82.8 plus b, where b is 1.91, multiplied by x. This is our equation. Now, this equation right here is our estimated equation. Remember, this is just allowing us to be able to estimate y values based on x values. This is our estimated equation. This is our estimated line of best fit. This is the estimated line of best fit. So, Jamie, no longer are we just going to just randomly select a line in between the points. So if you were to go ahead and plot these points, you know, we would roughly just put in a line in between majority of the points there. And then probably if you find the gradient of that line, you probably get 2, 2.2, 1.7, those values. But based on our calculation, this would have been the best line of fit with a gradient of 1.91. So you say we can find the line of best fit now.
So,
And then you just put this in Excel and plot the graph. You can just put an equation of graph straight into Excel to make it plot this. So you wouldn't have to worry about anything to get the best fit line pop up on the graph. So now that we have this out of the way now, I'm just gonna write it here. We end up get that y hat was 82.8 plus 1.91x. Now, Jamie, look at this now. This is the equation right here. I want to show you that you can even check it when you have different x. When x is 44.5, y was 168.3. So look at this. If you were to just plug in x as 44.5, you can check it. Like check in when x is 44.5. You get that the y value would be 82.8 plus 1.91 times 44.5. Notice that that y value would give you 167.8, which is roughly the 168.3, right? It's an estimate, but the line of best fit won't give you the exact y values, but it's going to estimate a close y value for almost every x value you can input, right? So that is that. So that's the line of best fit right there that we get. So scatter plots are really nice. The points all over the place, and we get our best fit using those three formulas we must remember. So if we go back around here, we could tell them that y is equal to 82.8 plus 1.91x. In the next case now, it says an anthropologist wants to find a femur of length 58 centimeters tall. How tall was the person? So in that case now, if the femur x is 58, y is just going to be 82.8 plus 1.91 times 58. This person, no man, this person well tall. I'm sure they're over 6 feet by far. 82.8 plus 1.91 times 58. Yep, 193.6 centimeters. So this person well over 6 feet. This person is like 6 feet 3, 6 feet 4, maybe closer to 6 feet 5. Yeah. That would be this person's height. And that's how you use it to predict. So they love to ask. So typically they love to ask questions like these. But in an exam, Jamie, I'm going to show you how they ask it in a past paper. I sent you in the notes. Make sure to, this is the formula that you
Can
use.
you send the PowerPoint? So
Send
that's
this,
example.
repeat.
Can you send the PowerPoint that you were working with?
Oh, definitely. Yeah, let me save it. Yeah, let me save it. Yeah, definitely I should. This is scatter plot 1. All right, because that's for today's scatter plot 1. All right, I just saved it. Save it as scatter plot 1. All right, yes, definitely as soon as we end, I can send it.
Sure.
Yeah.
For my scatter plot, I would be plotting the actual centimeter values, right?
Yes, you're going to be plotting your values. So let me bring up your IA. Let me open your IA and I'm just going to discuss what you're going to do. Open your IA.
To see how a scatter plot looks as well.
Yeah, download. You're going to be plotting your points. So let me show you now. All right, my Word document, Word loading very slow. I think I have too many programs open. Try and close some. What else I don't need open at this point? All right, come on now, stop it. All right, here we go. So we're good now. So here, all our tables right here. So let me just look back again. we're looking at wingspan to height ratio. We're looking at human body evolved, such as the result, proportionality, wingspan, correlation between wingspan and height. Very good. So we're looking at wingspan versus height. All right. So in this case, we want to predict, maybe height with wingspan, but we're trying to disprove that it's not in a 1-to-1 ratio. So in this case, our y value is going to be our height, and our x value is going to be the wingspan. All right, so x value is wingspan, and y value is the height. All right. All right, so let me look at the wingspan that you worked out. Here's the table, the wingspan. So these are all the x. You're going to plot all of these on your x, plot all of these on your y. All right. Based on what I'm seeing, it's going to be positively, well, I can't even tell. It's too many data points. So you're going to plot all of these x and all of these y's. That's the first thing you're going to do. You're going to get some points looking. Let me go back to a blank document. Let me come back here. I'm just showing you what your graph might look like. Might. I notice you have persons that are like 160 centimeters, a little bit shorter. Their wing. Let me see. Go back to the data. You have persons like 157, wingspan is 161. So height on the Y, height here, this is what you're gonna have, height. Then of course you have the wingspan. All right. Now, how you're gonna typically disprove it? You're typically gonna disprove it by showing that it's not going to be. If it is extremely strong correlated, then it would have a R value to be 1. When the R value is exactly 1, that will definitely give you that it is in a 1-to-1 ratio. All right, but chances are you're going to get a value between 0.7 to 0.8, indicating that it's strong positively correlated, but it is not extremely strong positively correlated. Chances are that's what you're getting from the 30 data, based on what I can eyeball. So maybe some person wingspan was 162, and I see somebody height was 157 to match up here, and probably have a next person at 162 wingspan, but maybe their height gonna be here. So I'm just putting some rough points of what you're gonna maybe get. From the 30 data points, it may look something like this. And you'll be able to get your line of best fit using the calculations. So remember the 3 equations that you need, Jamie. The first equation is, remember, y is equal to a plus bx y hat. And remember the second equation is b, the gradient is found by r times the standard deviation of y over the standard deviation of x. And remember the third equation is the formula for r, the long equation. All right, then that will give you your line of best fit. Once you get your line of best fit, once you plot the points, so plot your points in Word, make sure you input the points then, and then after you get the line of best fit, then you can, I don't know which technology you're gonna use to plot the, can you plot it perfectly in Excel, the line of best fit?
Not sure, but we can.
Yeah, I was wondering if there's a case where you can, after you get your line of best fit, just plug in y equal whatever. So it plot it perfect for you, just that straight line. After you work out that R value, you're going to tell them whether it is strongly correlated. We already know it's going to be positively correlated. You just need to tell them whether it's strong, positively correlated, moderately correlated, or whatever. And after you do that now, you can use, what I want you to then do is, you're going to use 3 data points. This is what I want you to do. You're going to use 3 data points from your best fit line. Meaning, once you get a best fit line, Jamie, you're no longer going to use the 30 data that you have. So you can either use somebody wingspan. What if somebody wingspan was 200? Check if somebody wingspan is 200, if the height is 200. Check what Y value you're going to get based on your data points. So use 3 data points from your line. Maybe use a point here, and another point here. Because what you're trying to prove is to show it's not going to be one-to-one. So using your best fit line, you're going to show that when you work that out, you probably get the ratio is, maybe the first here is 195 over 200. Maybe the next one going to give you, I don't know, maybe 180 over 177. Maybe another point. Just use some data points that is not from your sample points. Sample points are the actual data you have. Sample points are actual data. I want you to then use your line of best fit to pick X values to find the corresponding Y values. You get what I'm saying?
So,
And after you use that, you're going to disprove that it is one-to-one. All right? Yeah. So here
can
you
you send
show,
that file as well? The one you're
repeat.
writing? Can you send that file as well?
Oh, you want me to send this?
Yeah.
All right, no problem. All right, I'm gonna have to save this one. I'm gonna rename this. Let me see. Save as scatter plot 2. All right. So before we close, of course, Jamie, now I want you to do a question for me now. So now, is it fair now? I'm gonna allow you to share. Just gonna do one question. I want to see you actually perform all of these computation now. So then I know that you're good. All right, so something similar to this one, because we're looking at tackling the SPA. So I want to make sure that you're able to find Y good. And yeah, so the question, I don't know if you can open back that document, but I'll read out the point them to you. So the X values are, you want to write out the table? High temperatures,
Actually, just open the document, which
oh yeah, it is linear regression worksheet 1. And you're going to tell me what is your X and what is your Y. Very good. Anything that you're predicting, that's going to be Y. Yeah.
should I go over to a whiteboard Most for
Yeah,
most.
you can go over to the whiteboard. Yeah. Yeah, 'cause I know it would be difficult to work out those calculations there. Do you notice anything about this question, Jamie? Just by looking at the raw data, do you notice anything?
Not yet, honestly.
Hard to notice anything, right?
Yeah.
Good. And notice the sum of that is 0. Before I
Okay.
even continue, because I just check it and make sure it's 0. If you were to plug in 0 in a numerator, what gonna happen to R?
Also be 0.
What this gonna tell you?
That means there's no correlation.
No correlation. Very good, very good. Nice. This one was a straightforward one, no correlation.
So you can't put up this fit or anything.
So in this case, very good. We cannot predict. We cannot predict. Very good. We cannot predict. Since this one was so stupid, I want you to just do the third one before we close in quickly. The third one. This one was one of the easy ones. So do number 3. That one was so stupid. So identify your X and identify your Y. 9.5 minus 8.35, that's 1. No correlation again. Why giving so much question with no correlation? I check it and add it. All right. All right, Jamie, no problem. No problem for getting no correlation. All right. Now, there is a case now, as you can see with raw data. Sometimes you're going to be many times you're going to be getting no correlation with this formula. So that is why typically we don't necessarily use that formula. We use it when we have large data, when you actually carry out the experiment. That's the usefulness of that formula. But as you can see in the anthropologist case, that's an actual experiment. Now, when we don't carry out experiment, this is the formula that we're going to use, which we're going to be looking at tomorrow, which it's a lot more practical because a lot of question when you're going to get, when there's no correlation, you're going to just get 0 with the proper formula, which should be right? When there's no correlation, it should just be 0, right?
Yes, sir.
But with the other formula we're going to learn tomorrow to find correlation, well, we're still going to get a B value. Then we can find the standard deviation of Y over the standard deviation of X. We're going to use this formula tomorrow. You're going to maybe get 0.000015, but you're not going to get 0 because you're not finding X minus bar X. Because you're always going to have an X to evaluate the sum of it. You're always going to be able to evaluate the sum of Y. It's just that in these cases, it would just be really, really small. From the 2 examples that you did, right? The correlation would just be 0.000 something, right? You get what I'm saying, Jamie?
Hello? Yes, sir.
Yeah, so because we know that these would never give us 0, the sum of X and the sum of Y's will never give us 0. We're just saying that tomorrow, when we're using this formula, we're going to do back these same questions, but with this formula now. For the ones with no correlation, you're going to be seeing like 0.000 something, or maybe 0.1. But we know it is very weak correlation or no correlation when it is less than 0.3. So using the more practical formula tomorrow, when we get small data, 1, 2, 3, 4, 5, 6, 7, 8. In general, we categorize small data as anything less than 20. So like your SBA, which is 30, that's definitely large data. And so large data, you use the formula there. So you will get a correlation. So remember for your SBA now, Jamie, you have a lot of work to do right now, my gosh. So for your SBA, first and foremost, you're gonna plot the points now, plot the graph. Just clicking on scatter plot tool right here. I'm gonna send this to you. So you're gonna plot your points. After you plot your points now, you're gonna then work out all of this. You're gonna find the line of best fit, and to find the line of best fit, you use these 3 hell of a formula, type in equation and all of that, whole heap of work. And then of course, you're going to use at least minimum. You can use more. We use a minimum of 3 points from the line of best fit. That's not from your data set, to then work out the corresponding height for any given wingspan. Then you're going to work out the ratios and show them that it is not 1-to-1. All right?
All right.
Yeah, so when you finish, you can send it to me. Let us look at it. But it's tomorrow, right?
Yeah.
You have so much money, it wouldn't make any sense. So you're probably going to bed really late today, don't it?
I don't think it will take that long.
Won't take you that long?
Yeah, I can just drag to calculate everything for Excel, and then it's just typing up the rest.
Okay. All right. All right, as long as it doesn't take you too long and you're not missing out on too much sleep. So tomorrow we're going to continue with regression. And I know we'll pause a little bit, but we have to get rid of the IA first. Once we get the IA out of the way, then we can go back to, of course, probability, finish tricks, and stuff like that, right?
All right, well, thank you, sir.
Yeah.
I'm just in the PowerPoint with this one.
Yeah. Yeah, I'm going to send it right now with this scatter plot 1 and 2, all right?
All right.
All right, Jimmy. All right, so take care.
Yes, sir.
All right.